Okay, dear students, let us now discuss a few examples about moment of inertia. Okay, so in this figure 5.17, you are seeing one L-shaped figure for which you are asked to find out the moment of inertia. Okay, so previously we discussed the same example for finding out the center of gravity for this figure. So you remember that we divided this L section into two rectangles. Okay, and we found the areas of each of the section, and also the distance of each of the CG of each of the area, because CG of the rectangle is very simple to find out, means it is lying on the center, at the center point, okay, of the rectangle. If you meet the two diagonals, and the meeting point of the diagonal will be the CG of each rectangle. So that is pretty easy to find out. Now, in that example, we use one table. Okay, so the table is about finding out the area of each rectangle. For example, this is a first section of this L section. This is the first rectangle, and this is the second rectangle. So if you remember, we found the areas like 8 into 1 is equal to 8, and centroidal distance x from mm. That means this is a line from which the distance of the CG of the first rectangle is 0.5, because the total thickness of this, or length of this rectangle is 1 cm, 1 centimeter. Okay, then about this line LL, the CG, that means the center point of this rectangle here with the 8 centimeter length will be 4 mm, 4 centimeter from this LL, so which is also recorded over here. And you can find out the multiplication of ax and ay, which is written over here. That means 8 into 0.5 is 4, and then you have 8 into 4 is 32. And similarly for the other triangle, which is the second triangle with the length of 5 and thickness of again 1, okay, or height of 1. Okay, so for this also we'll find out the distance from this leftmost line as well as the bottommost line. That means mm and ll. Okay, so these are mentioned over here, and similarly you find out the ax and ay for this rectangle, and finally you sum these up for sigma ax is equal to 21.5 and sigma ay is equal to 34.5. And accordingly, by dividing this these figures with the total area, you can find out the x bar and y bar, which is representing the CG position of the CG of this L-shaped lamina. Okay, now we have been asked to find out the moment of inertia of this L-shaped lamina. Okay, you remember that we discussed about the moment of inertia of a lamina, about its CG. Okay, now for this rectangle, which is 8 by 1 rectangle, the first rectangle, the CG lies, you know that the CG lies at, passes through this center point of this rectangle, which is 4 mm above this line L and 0.5 mm away from this line mm. Okay, center point of this, which I am indicating with the cursor. So the moment of inertia is BD cube by 12. So B in this case is 1 and D is 8. Okay. So you get B into D cube. D cube means 8 into 8 into 8 divided by 12. So okay, so b is 1 centimeter over here. Okay, so you can see that 1 into 8 cube divided by 12. Okay, now using the parallel axis theorem, because we want to find out the moment of inertia of this L-shaped lamina about an axis which is passing through its CG. Now remember, CG of this rectangle, that is the first rectangle, and that of the lamina, L-shaped lamina, that it means combined figure 1 and 2, is different from the CG of this first rectangle. Okay, so you already found out that this is 1.65 and 2.65. So you can find out the distance of CG of this rectangle with this line XX, which is representing the CG passing through the CG of this combined lamina, L-shaped lamina. Okay, so this we can apply the parallel axis theorem here. That means moment of inertia of this rectangle 1 plus the area into the distance square. Okay, so this is 8 into 1 into 4 minus 2.65, because the distance y of this CG from the line LL is 2.65, so this whole square. And by using the similar procedure, we will find out the moment of inertia of the second rectangle, which is 5 into 1 cube, because 5 is the base and 1 is the height, so BD cube by 12 plus 5 into 1 again area of this rectangle into the distance, that means the distance of this point 2 from this point, from this line xx, which is nothing but 2.65 minus 0.5 square. So this is comes out to be total after you sum these up. This is a total moment of inertia when we are of this L-shaped lamina about xx, okay, which is passing through its CG. And similarly, you can find out the Iyy, which is the moment of inertia of this lamina about this line mm. Oh, sorry, about the line which is passing through its CG, and but a vertical line. Earlier it was a horizontal, so line YY. So again, using the same procedure, you can find out this. And if you are asked to find out the moment of inertia about the z-axis, z-axis, which is passing through the x from the CG, and which is perpendicular to the plane xy plane over here. So that also, using the perpendicular axis theorem, you can find out that. Okay, and there are similar other examples which you can easily solve using the procedure that I discussed and given in this book. For example, 5.2, again you will divide this T section into, or T shaped lamina into two rectangles, and find out their CG of this T section, find out the moment of inertia of this rectangle, of the second rectangle, and noting down the distance from distance of this CG of each of the rectangle from the common CG. Common CG means the CG of the T shape altogether. Okay, so you can easily find out the this is a solved example. Again, you can do some practice on this, and using the procedure you can solve any such kind of problems which are given over here. Okay, thank you.